Okay, hello
Yep.
everybody. So when Roland called me yesterday to jump in for Nana, who was ill, I was a little bit hesitant first. I said, but I'm not a quantum chemist. And he said, oh, it's okay, you're theoretical enough. And my colleague Peter said, just throw in an orbital and it'll be fine. But unfortunately, I don't have one single orbital, but hopefully I can interest you enough anyways. And my research is on a very different level of theory compared to what has been presented today, focusing mostly on ion diffusion mechanisms on the atomistic up to mesoscale level. So, and in any case, I'm happy to be here, and I'd like to thank Roland for giving me the opportunity to present to this audience today. And here at Uppsala University, across the road, as said, my team and I stand with one foot in the computational materials chemistry group, where we focus on application and development of multiscale modeling methodology, and with the other foot in the Ångström Advanced Battery Center, which is a world-unique environment for fundamental and applied battery research. And today I'm going to present some of my research, which focuses on the development of multiscale modeling approaches to predict and understand ion diffusion mechanisms in solid-state electrolytes. So, transitioning from volatile and environmentally hazardous organic electrolytes to solid-state electrolytes can bring a lot of benefits in terms of safety and stability and improved energy density of a lithium-ion battery. But synthesizing these type of solid-state electrolyte materials with high enough lithium conductivity has been a real challenge to develop these materials. So solid-state electrolytes are really a broad range of materials where we on the one hand have inorganic ceramic crystalline materials, and on the other hand we have soft, flexible polymers, which tend to have much worse possibilities of ion conduction compared to the ceramic materials. And we also have composite materials mixing both of these materials to improve the flexibility, the mechanical properties of the material, in addition to the ion conductivity. So in these different materials, the diffusion mechanisms are very different, and so they also require quite different approaches to be able to understand and optimize the conductivity. So I'm going to be focusing mainly on the development work, towards ceramic electrolyte, which my team and I have been working on over the past couple of years, and then I'll say a few words on how we're working now to extend our methodology towards polymer electrolytes, and then how we in the future would want to extend our multiscale framework towards more complex and multi-phase composite electrolyte materials. So, understanding how the variations of structure and chemistry affects ion diffusivity is very important to be able to optimize the electrolyte performance. And here, modeling, of course, plays an important role to provide an atomistic level insight and the possibility of systematically studying a broad range of materials and screening through structural databases of high-performing materials. And for ceramics, for example, these types of screening studies have been carried out for static energetic properties, such as band gaps within the materials project at Berkeley, for example. But for diffusion, this is much more challenging because the state-of-the-art methods like molecular dynamics are limited in time scales, and to be able and they're not sufficient to be able to probe diffusion in the vast majority of materials that we would like to be able to study, which makes screening using these methods very inefficient. And to be able to reach kind of a multi-phase range of the diffusion, this is really unfeasible. And in addition, the chemical space of the ceramic electrolytes span most of the periodic table, which makes the possibility of parameterizing inexpensive classical force fields quite challenging, and the transferability is really poor between these types of methods. The transferability and accuracy for these types of force fields are very poor, and this means that we need to go generally to a DFT level of theory to study the broader range of materials, and this additionally increases the computational cost of being able to compute the diffusion at an ab initio molecular dynamics level of theory by many orders of magnitude, which then really limits the number of the range of materials that we can probe the diffusion into only the very, very fastest ion conductors. So to be able to reach a broader range of materials, we need more efficient algorithms. So lattice-based kinetic Monte Carlo methods are used quite extensively for studying diffusion processes in crystalline materials where molecular dynamics isn't sufficient. And the hopping type motion, which is characteristic for the crystalline diffusion within this spatially rigid framework, makes a lattice model ideal. So this approach allows us to extend from the kind of constant time step molecular dynamics approach, where in the simulation, the sampling has spent most of its time just moving within the energy minima, to instead, on a lattice-based model, it only explicitly samples the transition between one energy minima to another in just one single simulation step, independent on the time that the actual process is expected to take. So the ion transport through the lattice is propagated randomly according to the probability of each process to occur relative to all other possible processes in your system. So to compute the probabilities of each possible transition, we need information about the different energy barriers. We need information about all the different energy barriers of transitioning from one energy minima to another. And this is, of course, where the big challenge comes in. How do we get these energy barriers? So the most common approach is to compute energy barriers by identifying the minimum energy pathway using, for example, the nudge elastic band method. And this approach often works very well when you're looking at individual systems or you're looking within structural groups, which where you know already beforehand the topology of the potential energy landscape. So because with the nudge elastic band method, you need to know where are the energy minima and the approximate transition path between them. So this really limits the applicability for extending towards materials where the transition state landscape is not already known beforehand. So this is a challenge that I was working on during my postdoc period at EPFL, where I developed a cost-efficient and automated approach to be able to map out a diffusion model for a mobile particle within any kind of crystalline structure without needing to know the topology beforehand. So the way it works is that we take a our coordinates for our crystal unit cell, and then we take our lithium, and then we just simply map sample on a regular equidistance grid the potential energy landscape, the potential energy that the single lithium ion feels within this three-dimensional space, void space of our crystal material. So this gives us this single particle potential energy grid, and then we use this as an approximation for our transition state landscape for the lithium, for the mobile particle. So here we're just talking about any general kind of mobile particle, not specifically lithium. And then we carry out a topology-based analysis on this potential energy landscape. So simplified, the topology, this analysis is a kind of an advanced flood fill type algorithm where it partitions the potential energy landscape into energy basins and the transition state surfaces that divide the energy basins. And then by using a transition state theory formalism, we can reduce the potential energy landscape to lattice sites and the transition rates that of jumping between the lattice sites. And this is the input that is needed for the kinetic Monte Carlo to compute the diffusion coefficients. Okay, so this method was first developed for studying methane diffusion in zeolites. And for the inert methane gas molecule, this single particle model is a very good approximation, and we can use inexpensive force fields sufficiently to allow us to compute accurate diffusion coefficients for methane in nanoporous materials in only minutes on a desktop computer. And what we have here is the comparison of our we call it the two-trust approach versus the atomistic level molecular dynamics simulation, so this is for different nanoporous materials at different temperatures, and we get a quite accurate prediction at a very low computational cost. But when I moved here to Uppsala and started to look at electrolytes materials, and I tried to apply this approach to ion diffusion in ceramics, the results really did not look very good at all. And this is since a single particle model fails due to the strong ion-ion interactions. So we then proceeded to correct this by adding an extra kind of Metropolis Monte Carlo routine, where we load our three-dimensional energy space with charged particles, our lithium ions basically, and just allow them to run a Monte Carlo simulation within this energetic space, and where the ions only interact with each other with the Coulomb interaction. So this is the output of this gave us this multi-particle potential energy surface, which really improved the prediction of the potential or free energy landscape, which is felt by the lithium ion. And then this multi-particle grid, in the same way as before, is then is analyzed by the topological analysis to create our lattice model and compute the diffusion coefficients. And here we got a significantly increased prediction of our diffusion coefficients in the ionic material. Okay, so with this grid-based method, the computational cost is significantly reduced compared to molecular dynamics, but to be able to approach experimental accuracy, a DFT level of theory is necessary, and if we also want this approach to be practically feasible for studying large numbers of materials, we need to reduce the number of explicit energy calculations for constructing the initial single particle potential energy surface without losing accuracy. So what we basically want to do, what we basically do is that the lithium is, we construct our single particle potential on the DFT level of theory, and then the multi-particle correction is a classical Coulomb interaction. So to accomplish this, we accomplish this basically by exploiting the symmetry of the ceramics, where we only need to compute once the energy of the equivalent sites. We exclude inaccessible and high energy regions of the potential energy surface, so we avoid sampling regions where it's very low probability of where the lithium is going to reside, and which has will have a very small effect on the diffusion outcome. And we use interpolation schemes that allows us to compute the potential energy surface accurately, but to a lower grid resolution. And together, these tools reduce the number of explicit grid calculations by 2 to 3 orders of magnitude. And we're currently looking at how machine learning can help to reduce this cost even further, such as by applying foundation models. So the next step is then to validate how this, now that we're able to compute these diffusion coefficients at a manageable cost at a DFT level of theory, we need to validate them towards DFT-based molecular dynamics. And the biggest challenge of validating these, of this validation is the high computational cost of performing the DFT-based molecular dynamics. And its limitation to only be able to probe the diffusion for the very fastest ion diffusers. So we're really in a very limited range of diffusion coefficients that we can validate against. So what we did to at least accomplish this is that we looked through the literature for all previously studied highly diffusive materials and ran the DFT molecular dynamics simulations at 1,000 Kelvin. And you need to run these simulations at that high temperature to be able to reach a diffusive regime in ab initio molecular dynamics. So we got converged diffusion coefficients for around 15 structures, and which we could validate our results from. And here all structures that we looked at were accurately predicted within the kind of 1 order of magnitude range that we're shooting for this screening approach. And if we then take a look at one particular structure, which is probably the most famous ceramic ion conductor. It's one of the materials that was first identified as a superionic ceramic conductor, and has a conductivity in the ionic conductivity in the size range in the order of what you would get in the liquid electrolytes that are currently being used today. So this is the LGPS. And what I'm showing here we have the LGPS structure, and here we have the trajectories from the diffusing lithium ion from the ab initio molecular dynamics simulations, together with the free energy landscape of our constructed by our ionic two-trust approach, and then we can also take this trajectory and convert it to a free energy grid for a more direct comparison. So we see here that the diffusion landscapes are very similar to what we predict, and so are also the diffusion coefficients in the different directions, and also the activation energies, which correspond well with the experimental values for this material. And okay, so the benefit is, of course, that this ionic two-thrust approach does this around 3 orders of magnitude faster. But what's particularly interesting is that these results also provided new insights into the diffusion mechanisms. And this paper from 2017 was the first to attribute the fast diffusion of this LGPS material to, in addition to a few other superionic conductors, to the so-called concerted motion. And concerted motion is when the ions move simultaneously in a kind of liquid-like chain motion. This hypothesis was supported by nudged elastic band method, the nudged elastic band calculations. In the first case, what they did is that they computed the minimum energy pathway for a single lithium ion, which gave one potential energy landscape with quite high energy barriers, and then they did this for several lithium simultaneously moving over the barriers, which decreased the energy barriers significantly. So since then, this hypothesis of concerted motion has really been established since then, that this is necessary to reach for a superionic conductor, that there is this type of concerted motion. But the interesting thing is that we actually see the exact same thing from our single particle when we go from our single particle potential energy landscapes, where the highest energy barrier is 0.5 eV, and when we go to our multi-particle potential, where the highest energy barrier is 0.2 eV, which is exactly what they predicted. But the thing here is that our model is a mean field model. So we would not be able to model explicitly the concerted motion process, which they are claiming is, which has been claimed to be necessary. And this means that the low diffusion barrier of LGPS and other materials can in fact also be explained by the configurational entropy that we include in our model of the mobile and interacting lithium ions. While these two different viewpoints of the configurational entropy and the concerted motion might not necessarily contradict each other, it does indicate that we actually don't need to explicitly consider this simultaneously transitions. But we can also, this is also reproduced by average mean field of the configurational entropy of the interacting particles. Okay, so now I've talked about our recent work on the ceramics, and I will now just say a few words on how we are trying to work towards the development towards understanding the method development towards the polymer type ion diffusion in the polymer electrolytes. So understanding ion diffusion mechanisms in solid-state polymers bring completely different type of complexities, because we have these very flexible polymers, and the flexibility also plays an important role for the for the ion transport, where the segmental motion of the polymers contribute to the diffusion process. And so the issue here is that, so what we want to do is to see how can we construct this kind of like probability-based model to this type of materials, and how can we make use of the perspective of the potential energy surface. And as the polymer lattice isn't fixed in space, like for ceramics, we can't map out the potential energy landscape in real space in the same way that we do with the ceramics, but instead we need to redefine the potential energy surface to spatially invariant reaction coordinates. And so one example of this is the coordination space that for the lithium to coordinate to different parts of the polymer, and to also to the lithium salt anion, which is also part of this polymer electrolyte material, and all of these parts play an important role in the diffusion mechanisms. So the idea here is that we can kind of restrict the potential energy landscape, or create a more fixed lattice-based model in the coordination space rather than in the real space. And here this coordination space can be mapped out, or the potential energy landscape of the coordination can be mapped out quite efficiently with Monte Carlo based sampling, which allows us to extract the transition states much more efficiently than we would be able to do with molecular dynamics. And from this model, then the idea is to apply, to use time-dependent random graphs from the distribution of probabilities from this math and this, or from this potential energy landscape. And this is a collaboration that I have with my collaborator Senja Bartel, who's a mathematician at BU and works explicitly on these things. So that's something we are working on. And one of the main benefits of these approaches, both for the ceramics and for the polymer here, is that we convert the different processes into the kind of universal language of probabilities. And the power of this is of using, expressing the different processes and probabilities, and using, for example, a framework like kinetic Monte Carlo, is that we, in a fairly straightforward way, can combine different diffusion processes, although they may occur on very different lengths and time scales, or are described on very different levels of detail. And what we hope to be able to accomplish in the future is to build kind of like an adaptable multi-scale and multi-phase modeling framework that can combine the dynamics of different phases and give into a mesoscopic transport model, where we can also test the sensitivity to different variations in the material in a pretty straightforward way, and identify different rate determining properties without actually knowing the true processes beforehand. And then the idea is that we can systematically study the mesoscale diffusion processes throughout the complete composition of multi-phase composite materials in order to understand how to design the optimal the optimal electrolyte material. And with that, I would like to thank all of you for listening, and I'd like to thank all of my colleagues and collaborators. And yes, thank you.
Thank you very much. Maybe we can one question. Something there. If someone I would be interested in organic electrode materials, but we can take that. Yeah, Joe?
As far as some of these systems goes, what's like a typical, what's the biggest persistence length you could talk about here?
Sorry, I didn't.
What's the biggest persistence length you could talk about here that would be sort of amenable to these methods?
You mean how far you can?
Yeah. Yeah.
So this, for a kinetic Monte Carlo model, you mean?
Yeah.
I mean, I think that there's really no limit because you're just combining probabilities of different processes.
So in other words, here, what's the longest range of order you actually have, though? I mean, I'm asking.
In a composite material, for example. I guess micrometers, up to, micrometers.